felt better this morning already now that I'm like back on that. So we already started talking about this idea of abstract inner product. So it's like dot product, but it's also not quite the same as dot product. Dot product's just a special case of the abstract inner product. And I think we got all the way to page 4, number 4, right? Let's just talk about that a little bit. We were just verifying that this guy, so for the vector space C of 0, 1, continuous functions defined on 0, 1, you can define an inner product, so it would be an inner product of two functions. The elements of the vector space are functions, is the integral from 0 to 1 of f of x g of x dx. We were verifying that the defining properties of inner product are satisfied by this guy. And we got down to number 4, where we have to look at the inner product of a function with itself, which in this case is the integral from 0 to 1 of f of x dx. Of course, that's just the integral from 0 to 1 of a function squared. And so the details are written out here. I just didn't want to rush through it. Of course, the integral from 0 to 1 of a function squared has to be greater than or equal to 0. Because if you integrate a function that's always positive or 0, there's no way to get a negative value for the integral. Just think the graph of f of x squared has to lie on or above the x-axis. So the integral has to be positive. So that the positivity is not the issue. The issue is if you get 0 for the inner product of a function with itself, can that happen? How do you show that that happens if and only if the function is the constant function 0? So here's my logic, okay, and I think you can follow this on. Suppose the function is not 0 for some x in 0, 1. So somewhere in 0, 1, the value of f of x is not 0. When you square that function, so not the function itself, but the square, we're going to have some positive y value, some positive output. Not 0, has to be positive, right? So for somewhere, well, by continuity of functions, if we're positive at one point, we have to be positive over some interval. You can't just jump up there and jump back down. That would mean the function was not continuous. So who knows what's happening over here or over here? We know we could possibly be 0, possibly be 0, but we're dragged up at that point. Like that's maybe the worst case scenario for that function, where it's 0 at a lot of spaces, but it's sort of dragged up above the x-axis for a small interval. But then this means the integral from 0 to 1 of f of x squared dx has to be greater than 0, strictly greater. It cannot be 0 because we got that little bit of positive area there for the integral. And that actually satisfies our only if demonstration, and just really the argument goes both ways there. So a little bit of need to talk about the properties of a continuous function in order to make that last portion of item 4 work. Questions? Yeah, so working with this kind of integral application of inner product is something we'll talk about a little bit more today, a little bit more next week. Now, so continuing on, back to the more straightforward part of the handout. A lot of the properties of dot product in our N that we discussed in 6.1 can be generalized to general inner product spaces. And we use the same language, so with slight changes in terminology. I think our textbook says the norm of a vector V is going to be denoted like this with those double bars, and that's just the square root of the inner product of that vector with itself. Our intuition tells us is that this is length, but we'll talk a little bit more about the example. Maybe I'll wait till we get down below. When you have inner products defined in other ways than dot product, it doesn't look like length. Like, what does it mean for a function to have a certain length in a vector space where the elements are functions, all right? So let's just go in order with these points. The distance between two vectors is defined to be the norm of the difference, the length of the difference of those two vectors. A unit vector is a vector whose norm is equal to 1. So in an abstract inner product space, you can talk about like a function f in C01 having its norm to be equal to 1. It's a unit element of that vector space then. We say two vectors are orthogonal if the inner product of u and v is 0. So you can talk about functions in C01 being orthogonal to each other. And it doesn't really mean there's any right angles you can draw and see that perpendicularity. It just means that certain property is satisfied. So some examples here. I'm not working with a specific function. I'm just trying to help you see what this notation ends up looking like in these other situations. So if we, again, take that continuous functions on the interval from 0 to 1 and use this inner product that I've defined that involves integration, norm of a function is going to be the square root of the integral from 0 to 1 of f of x squared dx, whatever that creature is, for any continuous function on 0, 1. Should we just look at it? I don't have enough specific examples on here. And suppose f of x is x squared. What is? So that's like final exam question in this inner product space. And it's an easy problem if you just know what we're asking to do. But again, I would have people on the final just leave it blank, say, I don't want to do it. So we just plug into the formula. So it's the square root of the integral from 0 to 1 of x squared squared dx, and the square root of the integral from 0 to 1 of x to the 4th, right? Okay, that's the integral. You don't want that square root sign on the outside. It looks so intimidating, but it just means we're going to get a number at some point and take its square root before we're finished. So it's ready to integrate. That's x to the 5th over 5, evaluated 0 to 1. So I think I just get 1/5 minus 0, the square root of 1 minus 0, or 1 over the square root of 5. That, we would say, is the norm of f of x equals x squared. If that's our typical quadratic function, our favorite quadratic function in this vector space of continuous functions on 0, 1. It's just some number. That's how long we think that function is. But it's not like you can hold up a ruler and measure that distance. The distance between two functions is given by the norm of the difference, which is the square root of this, which is the square root of that, which again is just you calculate the integral, you get a number, you take the square root of that, we say that's how far those two functions are apart. So you kind of just go with the definition of what the inner product is and just apply these formulas. I think my plan now is next week we're going to go through some more specific examples of working with this, so you don't get spooked by this application. So, let U and V be vectors in an inner product space. We say that U and V are, or this is a theorem. Oh, here I go. U and V are orthogonal if and only if the norm of U squared plus the norm of V squared equals the norm of U plus V squared. So this is a generalized Pythagorean theorem. What does it mean for U and V to be orthogonal? That means the norm of U and V is 0, right? So we've already defined that. Here's an equivalence to two vectors being orthogonal, the Pythagorean theorem being satisfied. Of course, we can't draw a picture with a triangle. And the proof I don't write out here, it's absolutely identical to what we wrote out in 6.1. We worked through those steps. It's dealt with in a totally abstract way in 6.1. Now, next page. So theorems from 6.2 to 6.4 can all be extended to generalized inner product spaces. In fact, we could have started talking about an abstract inner product right at the beginning of the chapter, but I like our book's approach of putting the emphasis on dot product in Rn first, and getting used to that, because I think we have more geometric intuition about the dot product in Rn, but now we are going to have to apply those principles to abstract inner product spaces. So orthogonal decomposition, theorem 9 at 6.3, whatever that was. Related to that. And the Graham-Schmidt process from 6.4. So your homeworks you got back at the last problem you turned in was applying Graham-Schmidt to dot product in an R3 or R4 or something like that. On the final, I might ask you to apply Graham-Schmidt to this vector space of continuous functions on 0 limits. So that's the kind of problem we'll probably crack. Oh, there's one on the end actually. So, before we get down to specific problems of working with inner product in these various abstract spaces, there are two more results, two more really famous theorems that we're going to go through the proof of. One is called the Cauchy-Schwarz inequality, Cauchy-Schwarz inequality, and that theorem is used a lot in advanced calculus classes in upper level mathematics, and I'm sure it's probably used a lot in physics theory also. And one that has a much simpler name, but it's really just as important, something called the triangle inequality. And before we look at those, though, we need a little helping theorem, lemma you could call it. So let's go through this. And this, you should be able to follow all the reasoning here as we go. So we're going to go through it together. Let me know if anything's not clear. So W's subspace of an inner product space V. So let's maybe set things up kind of aside to abstract, right? So reigning overall is V is an inner product space, any inner product space. Inner product space means a vector space with an inner product defined, and W is a subspace of V. And let Y is any vector in V. So it's sort of the mother space, the encompassing space. Here's an interesting result that I think intuitively makes sense, but how you would show it isn't so obvious. The norm of the projection of into W of the vector y is always less than or equal to the norm of y. This is something we've also been calling y hat. So if you, but it's nice to use the projection notation here. So we're saying if you take a vector y and you project it into some subspace W, this is where the projection would be in my simplified situation that I keep referring back to over and over because I can draw the picture in that case. And this is not actually an abstract, this is more the dot product situation. What this is saying is the length of the projection is always less than or equal to the length of the vector line. And that is kind of how projections work. A projection is never longer than the vector you started out with. When you project into a subspace, you either get shorter, you could possibly be the same size, right? Y might start out being in W in the first place. In that case, the projection is going to be Y, the norm or the length is not going to change. All right? So, okay, I believe that. So the norm, the length of the projection of Y into W is less than or equal to the norm of the length of Y. Here's our proof. So what is Y? Y is the projection plus Y. What is the projection? So that's an easy statement to write down. This first guy is Y hat in some of our other notation. This is a vector in W. Okay? When we take the difference, we're always going to get a vector in the W perp. Okay? That's like our Z that we've been writing down up to now. So the projection into W of Y and Y minus the projection are orthogonal because any element of W is orthogonal to any element of W perp. So we can apply the generalized Pythagorean theorem. Okay, so if these two vectors are orthogonal to each other, the square of the norm of this guy plus the square of the norm of this guy is equal to the square of the norm of the sum of those two. So this is sort of like the U, the V, and the U plus V. But the U plus V in this case, when you add these guys together, just takes us back to Y. All right. So this is like norm of U squared plus the norm of V squared equals the norm of U plus V squared, which is just in this case norm of Y squared. And so it's got to be true that the norm of this projection squared is less than or equal to the norm of Y squared. We're taking out this term. We're just saying this term has to be positive or 0. So if we remove it, we have a quantity here on this side that's less than or equal to the quantity on the right, right? And we can take square roots of both sides. Now, you got to be careful when you take square roots of both sides of an equation. But if you know that we're squaring positive quantities, so the norm inside the square here and the norm inside the square here are positive to begin with. We can take the square roots then on both sides. The direction of the inequality is going to stay the same because we're working with positive quantities. So the norm of this projection is less than or equal to that, which I think is just what we want to show. Right? So that's a nice, straightforward application of some of this theory of product spaces and projections. So that's our little helping theorem. And our helping theorem just says a projection is always shorter than or equal to in length the length of the original vector. Now, something a little deeper. And this, I know when I was a student and I came across this thing, this was one of the most mysterious theorems I ever saw. And I've never really known a way intuitively to just believe this is true. So I always thought of it as a really powerful result because it gives us something that you would never guess had to be true necessarily. Okay, so here it is, Cauchy-Schwarz, this is one word, inequality for all u and v in an inner product space. So here's what it's saying. This is always true. The absolute value of the inner product of two vectors is always less than or equal to the norm of one times the norm of the other. So this is just multiplication of the real numbers. On the right-hand side. So it's sort of like saying one product, the inner product of two vectors in absolute value is always less than or equal to another kind of product, the real number product of the norms of those two vectors. And if I were you right now, I'd be saying, big deal. Because that notation is not terribly revealing of what's going on here. So we're gonna, oh, sorry. Maybe Siri knows. So let's go through the proof first, because I like this proof, and I think it's accessible, and it uses the stuff we've been working with. But then we're gonna look at some examples. This is Cauchy-Schwarz, but what the heck is this even saying? And we're going to talk about some examples I don't have right on the handout because I realize now this is kind of abstract for you guys. So here's our proof. If u is equal to 0, if u is the 0 vector, and both sides are 0, so the inequality holds. So that's one case. If u is 0, this inner product is 0, this magnitude is 0, it doesn't matter what v is, 0 equals 0, so it's true. So suppose u is not the 0 vector, then we can say a little bit more. We assume u is not a 0 vector. Let w be the span of u. So w is a one-dimensional subspace consisting of all scalar multiples of u, right? It's like a line in whatever abstract vector space we're in. We're not in Rn, we're in an abstract inner product space. Now, we can, now, u and v are two different vectors. So w is the span of u. We're going to project v into w. So we're going to project v onto w, which is just all these scalar multiples of u, right? So the projection is going to be some scalar multiple of u. And we have our formula for it, right? The scalar multiple of u that we get is this inner product of v and u over the inner product of u and u. Up to now, we've been saying v dot u over u dot u. In an abstract sense, we don't say dot product because that's other kind of notation. But it works just like dot product. The formula looks exactly the same. And so let's see. What is the norm of this projection? How long is this projection? So there's the projection. Well, it's just the norm of this thing, because we said that's equal to the projection. So what can we say about this? This is a scalar times a vector. When you take the length of a scalar times a vector, the length is equal to the absolute value of the scalar. We need absolute value because this fraction might be negative, times the norm of the vector u. And I can take this fraction apart into an absolute value over a non-absolute value because the inner product of u and u has to be positive, right? The inner product of any vector with itself has to be greater than or equal to 0. Uh-oh. What? Wait. Inner product of any vector with itself has to be greater than or equal to 0. What if this was equal to 0? You can answer. Can't be because we said u was not equal to 0, right? So that's why we took care of this case first. See how math works. We got that difficult situation, which actually was the easy situation to talk about. We got it out of the way. So then we were able to suppose u was not 0, and we need u not 0 to be able to use this formula and have this guy in the denominator and not be 0, right? So that all works out nicely. All right, so we have an absolute value of an inner product over just an inner product times, now we can rewrite this norm as the square root of the inner product of u with itself. That's what that norm is defined to be, right? And now, maybe I made too big of a jump here in the algebra, so let me write this out too. Because there's nothing going on here, but I want you to be convinced there's nothing going on. So I'm recopying this line. This is a real number divided by a real number times a real number in these inner product calculations. And we just said the inner product of u with itself is positive. So I could rewrite this as the square root of that inner product squared. So I have something like a over b squared times b. We just want to cancel a b, and we'll end up with a over b. That's the only magic going on there. So when I cancel a square root above and below, I'm left with the square root of b dot b below. So that's why this square root goes away, and we end up with just a square root, right? Because of this is some quantity, that's just the square root of that quantity. We're canceling out the square root. So now we get to here, and so now we're going to pull our helping theorem in to help us talk a little bit more about what's going on. So this is equal to the norm of the projection, right? From our helping theorem, we know the length of the projection is always less than or equal to b. So this is like our key step, because this gives us an inequality, right? So the projection of v into w, and I will just erase my picture of that, is always less than or equal to the length of v, norm of v. But we're going to replace this guy with this expression we just generated. We're almost done. And we're going to rewrite this denominator as the norm of u, because that's exactly what those symbols stand for. So we have an absolute value of an inner product over the norm of u less than or equal to the norm of v. We can multiply both sides by the norm of u. That's positive, so the inequality direction doesn't change. And we end up with what we want. Okay, we got v and u backwards here. We can just turn them around, because that's the same thing, right? The inner product of v and u, the inner product of u and v are the same. And so there's the Cauchy-Schwarz inequality. Okay, let's just leave this up here a second. And I want to talk about an example of this, which I should have had on now. Let's just think about what this means. Let's illustrate. This is not on the handout. Because if you're like, what the heck is all this abstraction? With the dot product in R3. I'm just picking a specific example. So U would just be a U1, U2, U3, three-component column vector. V is a V1, V2, V3, three-component column vector. The inner product of U and V, in this case, is just the dot product. So it's U1, V1, plus U2, V2, plus U3, V3. Now the inner product or the dot product of two different vectors could be positive or negative. So it makes sense to take absolute value. I mean, it's not always positive. It's only positive when you take the inner product of a vector with itself. But if they're different, it could be a negative. So that absolute value refers to the absolute value of that sum of products, right? This guy, all right, the norm of U, is just the square root of U1 squared plus U2 squared plus U3 squared. And the norm of V, this is just good old-fashioned length of a vector, right? The square root of the sum of the squares of the components. I guess some of you guys are in 110C right now, so it might not seem so old-fashioned. And so our inequality looks like this. Flash for color. U1, V1, plus U2, V2, plus U3, V3. An absolute value is less than or equal to the square root of U1 squared plus U2 squared plus U3 squared times the square root of V1 squared plus V2 squared plus V3 squared. Now, U1, U2, U3, V1, V2, V3 were the components of two vectors. Those were any numbers at all, right? Any real numbers. So this is actually true for any real numbers. It's actually true for any complex numbers too. U1, U2, U3, V1. So there are 6 numbers involved here, V3. And again, when you see it in that form, where you see this calculation with 6 numbers here is always less than or equal to this calculation with 6 numbers there, I mean, I can believe it, but if somebody said show that was true, it's not at all obvious how you might show something like this. I know when I first saw this formula, I think I first saw it in this form, and they were like, prove this is true for any real numbers, any 6 real numbers, and it's not. Let's just try to illustrate it with this even more specific example. And I'm just going to pick random vectors here, so who knows what this is going to look like. Let's do 1, 2, 3. B is -2, 5, 1. So what is U dot V is, well, let's do that just so we get a little more negative here. So U dot V is -2 minus 10 plus 3, which is -9. Okay. Magnitude U is the square root of 1 squared plus 2 squared plus 3 squared. Square root of 14. Magnitude V is the square root of -2 squared plus -5 squared plus 1 squared. 25, 26, 27, 29, 30. Is that square root of 30? All right. So what Cauchy Schwartz tells us here is that the absolute value of -9 is less than or equal to the square root of 14 times the square root of 30. I guess it's true. You can check it. You can verify all sorts of particular examples, and each time you're going to say, yeah, of course that's going to come out that way. But to me, the idea to verify this in generality, to prove that this statement has to always be true, if you just write it out in terms of components, what the heck is the relationship? Like, I know when I was a student, I tried squaring both sides, right? Like you think, well, what if you square this and square that? Can you just do all the algebra? And you get a big mess of algebra. It doesn't, I don't think that helps if you square both sides. And so just thinking in terms of numbers, it feels right, but verifying it, to me, here's this great example of using abstract math, which it just sort of, we didn't have to use anything fancy to get this result, to get this very surprising kind of not at all intuitive result about numbers called Cauchy-Schwarz inequality. All right, so got it out. This is 2 minutes. Let's turn the page. So another theorem that is a little bit more straightforward and a little bit easier to show than Cauchy-Schwarz is the triangle inequality. And it's also very important in advanced calculus. And it's much more intuitive. This is one where you'd say, like, of course it's true. And its little old name, it sounds so, like grade school or something, the triangle inequality, is just based on the triangle you can draw to illustrate vector addition. And there's a theorem from geometry, I don't know if they teach it anymore, but it's a very fundamental theorem about triangles, that the sum of the lengths of two sides of a triangle is always greater than the length of the third side. I mean, visually, it's just totally obvious, right? It doesn't matter which two sides you pick, the sum of the lengths of any two sides of a triangle is always greater than the length of the third side. And so you can think of this inequality in terms of a picture of a triangle where you think of these guys as the three sides of the triangle. But in terms of vectors, we're saying for any vectors u and v in an inner product space, the norm of the sum is always less than or equal to the norm of one vector plus the norm of the other vector calculated separately. So it's an inequality theorem, like Cauchy-Schwarz, and we can verify it just using properties of the product. So here we go. Let's see, the norm of u plus v squared. When you square the norm, you get the inner product of a vector with itself. If this is not squared, the norm is the square root of this stuff. So when you square it, it's like you're squaring a square root sign goes away. And then we can just use our distributive properties, just like in algebra, to pull this apart into the sum of four separate inner products, and two are equal. So we got the inner product of u and u, 2 times the inner product of u and v, plus the inner product of v and v. And then we can go back to our norm notation. The inner product of u and u is the norm of u squared. This we leave alone. This is the norm of v squared. And then there's sort of a magical step here, which wouldn't be obvious to me what was going on. So far, there's a lot of positive quantities here, but the inner product of u and v could be negative, positive or negative. So what we want to do is plunk down absolute value bars here, okay? So this turns into an inequality. Because the line above could be positive or negative, that's always going to be less than or equal to the absolute value of that quantity. And that's just a result about numbers that I think you know. A number A is always less than or equal to the absolute value of A. I mean, if A is positive, they're equal. If A is negative, it's less than or equal. So it's sort of a silly inequality. But that's the only idea that we're using to get from this line to this line. Okay. So the inner product is less than or equal to the absolute value of the inner product. And then we're going to pass through another inequality. We're going to apply the Cauchy-Schwarz inequality. So the funny thing is we need this incredibly powerful inequality here to get this cute little great little triangle inequality result, because we're going to say the absolute value of the inner product of U and V is always less than or equal to the product of the norms of the two vectors U and V. See how we made that change here? We're just recopying the other positive terms on both sides. So that's by Cauchy-Schwarz. And this guy is a real number squared plus 2 times the product of those two real numbers plus a real number squared. So we can just express that as a square of a binomial. And once again, we got a square less than or equal to a square. But since the quantities being squared are both positive, the quantities themselves, this quantity has to be less than or equal to that. And that's the triangle inequality. So again, I just like this abstract development because we had to use this strange Cauchy-Schwarz thing to get our crucial step to prove this triangle inequality, which intuitively seems obvious, but how do you really verify it's always true? Now, I'm almost out of time. So exercises, we're going to do one, so we're going to leave the next one, second one for next week, and we'll do more exercises next week. We're not going to do new material, we're just going to work with abstract inner product space and scary looking things like this, so that you get comfortable with it, because there will be something on the final exam that has to do with that 6.7. Oh, other thing about the final exam, before I forget about it too, and I'll remind you in the next few days, I will let you bring a sheet of notes. So just not Friday, only the final exam. And so you can 8.5 by 11, both sides. You can pay admin to fill it out for you because he has the world's smallest handwriting. He can fit more on a sheet of paper than anybody I've ever seen. But that's okay for the final, okay? So that, just so you don't feel like there are going to be so many of these results and weird notations and things that you can write it out. All right, so exercise, the first exercise here, let f and g be in C01. Show that this is true. This is true for any functions now. The absolute value of the integral from 0 to 1 of the product of two functions is always less than or equal to the square root of the integral of the square of the first times the square root of the integral of the square of the second. And there's like one line to say. Just say, true by Cauchy-Schwarz. All we're doing is plugging that inner product defined by into the Cauchy-Schwarz formula, and that's what it looks like, right, for the inner product of continuous functions 0, 1. So we'll write it down next week too. So Wednesday is our review for the test. We'll do some review problems. Friday's our exam. I'll get those back to you on Monday and Wednesday of next week. We're probably, I think we'll just talk about 6.7 mainly, but we can go back and address any questions you have about earlier in the course.